Friends, welcome to the online course on non-conventional machining or advanced machining processes. We are discussing about ultrasonic machining process. In part 1, we have discussed what is meant by ultrasonic. Then we have seen block diagram of working of USM system, and we have discussed the working principle of USM process. And also in part 2, we have discussed about various elements of USM setup, and we have covered the parametric analysis of USM process. Today in this part 3 we will discuss the effects of process parameters on the performance of ultrasonic machining process. Then we'll discuss the process capabilities of this process, and at last we will cover the applications of this ultrasonic machining process. So let us start with the first point, that is the effect of amplitude of vibration and penetration rate. So in this slide I have shown the relationship between the amplitude of vibration of the tool, and penetration rate, that is penetration rate of the abrasive particle into the workpiece. You can see here that as the amplitude of vibration is increasing, then the penetration rate is also increasing. But beyond the a certain value, you can see here, beyond the certain value, this is trying to become more or less stable. Okay, more or less stable. So the penetration rate increases up to a certain limit if amplitude of vibration is increased, but beyond this value it strives to stabilize. And as you can see, beyond this value, amplitude of vibration, if you increase, then penetration rate will stabilize. Okay, like this. A main reason of this is the constant force. Since the force remains the same or the constant, it tries to stabilize beyond a certain value of the amplitude of vibration. Okay, then a relationship between the frequency of vibration and the penetration rate is shown over here. Okay, you can see in this slide. As we can see, as the frequency of vibration is increasing, the penetration rate is also increasing, but it also tries to stabilize. Okay, you can see here. So as the frequency of vibration increases, penetration rate increases up to certain limit, and with more number of abrasive particles impact per unit time on that workpiece, definitely the penetration rate will increase. Beyond the maxima, it tries to stabilize, as you can see over here. Okay, then grid size. Okay, grid size is the another important parameter which affects the penetration rate. And as you can see here, as the grid size is increasing, there is an optimum value where you get the maximum penetration rate in terms of the mm per second. And here machining rate, okay, machining rate means the penetration rate, and it also increases up to an optimum value where you getting the maxima. And beyond the maxima, this one, it start decreasing because the force is constant at different grid size during the experiments. So as the grid size of the abrasive grid size further increases beyond this optimum value, the penetration rate start decreasing. You can see here. Okay. New parameter, that is hardness ratio. Hardness ratio means what? The ratio of the workpiece hardness and the tool hardness. Okay, this also hardness ratio plays important role, as we already know that As the hardness of the workpiece increases, the MRR goes uh, goes down. And you can see here also, as the ratio of the workpiece hardness and tool hardness is increasing, the MRR is in terms of per second is decreasing. It becomes more or less beyond the also beyond this certain value of this ratio. And if the hardness of the workpiece is very high, then MRR may decrease substantially, which is tending towards the zero. Okay. And as the hardness increases, MRR decreases, because here the penetration rate is the function of workpiece hardness. And if the tool hardness decreases, then abrasive can penetrate inside the tool to reduce the penetration rate in the workpiece. And as you can see here, if the tool hardness decreases, then this hardness ratio becomes higher, but the abrasive particle will penetrate inside the tool, and this will decrease the penetration rate. Okay, that is MRR. Okay, next one is the particle velocity. As the particle velocity is increasing, you can see here the linear machining rate, that is MRR, in terms of per second is increasing. We already know that the penetration is the function of kinetic energy, that is 1 half m square. So as the particle velocity is increasing, the machining rate is also going to increase. Okay, the next one is the abrasive concentration. As the concentration of the abrasive particles increases, you can see here it increases material removal rate, that is MRR, in terms of per second. Beyond a certain concentration value, it start decreasing. As abrasive concentration increases, the machining rate attain a optimum value. Okay, you can see here also. And if the concentration is too high or beyond the optimum, then due to the lower impact velocity and collision of the abrasive particle with each other, it will result in the reduction of this metal removal rate or the machining rate. Okay, then we'll talk about the static load. Load also plays an important role, as we can see in this slide. Okay, here static load is increasing, the penetration rate is increasing. It is in per second. Beyond a certain value of the static load, in both the cases of amplitude of vibration, it start decreasing. And as the amplitude of vibration increases, the penetration rate is also increasing, and the relationship between the static load and the penetration rate shows an optimum value. You can see it here. And the optimum penetration rate increases with the increase in amplitude of vibration. Okay, optimum penetration rate increases with the increase in amplitude of vibration. And this also can be seen that this optimum value is higher for higher amplitude of vibration. Now if you vary the static load as well as the tool diameter, then this kind of relationship we can obtain. And as the static load is increasing, penetration rate is also increasing, but beyond a certain value or the optimum value, as we have seen in the earlier figure also, it start decreasing. Okay, but as the tool diameter is increasing, then the penetration rate is decreasing, and increasing tool diameter decreases the penetration rate, because pressure decreases with the increasing tool diameter. Okay, as we know that general formula or basic formula, pressure is equal to force upon tool cross sectional area. Okay, now let us discuss the process capability. Already we have studied the effects of different parameters on the performance of the process. Let us see this capabilities of this particular process. And the process works better for the this process works better for the hard and brittle metals. The hardness normally recommended of the workpiece should be greater than or equal to Rockwell hardness on scale C as 40. Okay, HRC 40. And the material which can be completely machined include carbide, ceramics, tungsten, glass, etc. And the surface finish that can be obtained by this particular process uh, in the range of 0.25 to 0.75 micron. Okay, however, all this will depend on the selection of the parameters of USM process. Okay, if you talk about the accuracy, normally the holes that are obtained from the USM process have the conic shape. Okay, have the conic shape, and that is the shape of the drilled hole or the cavity is not straight sided, rather they are tapered. And to reduce the conicity, negative taper on the tool and the higher static load on the tool can be provided. And out of roundness in the hole is the major issue in case of USM. Okay, and the tolerances that can be achieved by using this process uh, is up to plus minus 25 micron. And upper limit of the depth of drill drilled hole is normally 51 but in very few or in very special cases user have gone up to 120 as the depth of penetration, but for this you require special kind of the slurry pumping device so that slurry can be deeply inside. An aspect ratio that has been obtained is normally 40 as to 1. Okay, let us discuss the process applications. This USM process can be applied for electrically non-conductive as well as conductive metals, because we are not making either tool or the workpiece as cathode or anode. It is a very good process for the hard as well as the fragile components of or the component made of hard and fragile material. There is uh, there is another very important capability of this process. Multiple holes or the multiple cavity can be machined at the same time, and it can be used as you can see here. This is a tool which is having more than one holes. Okay, more than one holes. And this is the shape that has been produced on the workpiece. You can see that there are the 6 big size holes are there, and 6 smaller size holes are there. All these 12 holes have been produced at the same time using this particular tool. Okay, using this particular tool. And this USM process also used with the uh, ECM, that is electrochemical machining, as we can call it as yeah, ultrasonic assisted ECM process. When it is used with the EDM process, that is electric discharge machining, we call it ultrasonic assisted EDM. Okay, when used with the ECG, that is the electrochemical grinding, it is called ultrasonic assisted ECG. Okay, so these are the some process cap applications of this process. This is a reference from which I've taken this material for the our lecture. Okay, thank you very much.
Hopefully you might have enjoyed the lecture. Then please do like the video and know your thoughts in comments. Please do share this video among your friends and don't forget to subscribe to our channel. After subscription you can press the bell icon to never miss the notification regarding our new videos. Thank you so much.